Check, check, check. Barbara.
Okay, good morning. My name is Sunil Kumar, and I have the privilege of serving as provost of this university. And as provost, one of my job responsibilities is that of a glorified doorman. So I go around to various functions and say, welcome. So that's my role here too. However, this is a testament to the Science of Learning Institute that even with my little corner of academia, there is a connection between the science of learning, in fact, some of the speakers today, and what I used to do for a living before I became a doorman. And this is, I teach a PhD course called Dynamic Programming and Optimal Control, and I've taught it for many, many years. And one of the modules in that course is called learning. And what we mean by learning is what Abraham Wald meant by learning in 1939, which is we have an idealized human being who can sequentially apply Bayes' rule without making a mistake over an infinite period of time. The advantage of making that assumption about humanity is that you get these extremely elegant mathematical prescriptions for what the answer is for many questions, for example, should I keep teaching the student or give up? Which is one of that is a homework problem in my course. And this actually in the 1940s was a problem that they studied. And when do we terminate education was a problem that people studied. It's called a stopping problem. And so, as you can imagine, in the applied math and stats department, that's where I am at Hopkins. And I knew, of course, all along that most of what I was teaching was hokey. But the way we got away with it was apply the prescription anyway, and it'll do reasonably okay as a heuristic in the setting you're interested in. And that seemed to work. At least the students went away. And so when I was preparing for this talk, I went through the Science of Learning Initiative's website. And I knew that there would be something that would directly contradict the hypothesis I was making about human beings in my course. And there is. And in fact, so I've learned something. So I just wanted to thank you for that. And this is a research award that the Science of Learning Institute gave out from 2017 for 2 years. And it's called Anti-Bayesian Updating, where not only is the assumption in my course not entirely applicable, humans actually do the opposite of what was assumed. So now this will be a homework problem in my course, in which case, because anti is okay, if they're doing the exact opposite, then you'll still get a nice prescription. And so we will, so you've given me at least a homework problem, but more importantly, I just wanted to make the case that this is proof that since I work in a tiny corner of academia, it is proof that you genuinely have a broad ambit in the university. It's a genuinely interdisciplinary endeavor, as today's program makes clear. Such endeavors don't come about without somebody or a group of people championing such endeavors, and there are two sets of people that I'd like to acknowledge today. First and foremost are our donors. I mean, we have several of them in the room today, and I'd like to thank them for their extraordinary generosity towards the university and the institute in making this happen. And the second person I'd like to thank is Barbara Landau. Without Barbara's vision over the last 5 years, I don't think this would have come along as far as it has done and remained as Catholic as it has in its academic endeavor. It would have gotten narrowed down, I'm sure, without someone who had the kind of broad vision that Barbara did. So thank you, Barbara, and thank you to the donors. With that, my role as doorman is done. Thank you also for the homework problem. And now I shall turn it over to Barbara. Please join me in welcoming.
Thank you so much, Sunil. I have to say it's a delight to be introduced by Sunil. I appreciate your comments, and I have to say it's a unique event in my life. I've never been introduced by a doorman before. So thank you for that. I'd like to welcome everybody who's in the room, and also people who are viewing online. We have many as 300 people who have registered for the event in person, and probably about 100 more who are viewing it online. That's been the typical draw of this symposium in the past. And I'd especially like to welcome you to what we consider a really exciting event to celebrate our 5th anniversary of the launch of Science of Learning, which was in January of 2013. And I have to say that I think we should celebrate today by declaring victory on our founding goals. And especially the founding goal that was to bring together people across the university in a unified community to study really hard problems, this one being the science of learning. The science of learning is founded on the overall goal that the mission is to understand learning at all levels of explanation, from the cellular, molecular mechanisms of learning common to all species, to the cognitive computations that are required for humans to learn their native language or understand the thoughts and intentions of others, to the, let's call it intelligent design of materials and settings that best foster learning in formal settings, such as schools and other training settings. And all of this is designed to optimize learning on an individual level, to enhance people's existing capabilities and to build new ones that will be suitable for the future. Now, to achieve this rather lofty goal, we've had the past 5 years have been guided by really determined efforts to focus on 3 particular goals. One is to support cutting-edge science of learning research. The second is to train the next generation of leaders in science of learning. And the third is to connect science with practice through partnerships in the community of educators broadly construed. And tomorrow on our website, you will be able to download or view a PDF of a book that we've created to celebrate our anniversary. For now, I'm going to give you just a peek of the accomplishments that we believe we've made. We have funded 41 innovative science of learning research and fellowship projects over the past 5 years. This has fueled 164 new collaborations across 6 divisions and 34 departments at Johns Hopkins. The seed grants just from the first 3 years have generated over $17 million in new funding for research and community partnership projects. This is on an investment of $3 million for the first 3 years. We have produced 13 community partnerships to develop educational programming and for teacher professional development. And we've produced 86 outreach initiatives to disseminate research to the broader science of learning community, and this symposium is one of those initiatives. The entire enterprise is absolutely an enormous team effort, and it's by the large and growing community at Hopkins who have been involved with this project over the past 5 years. I want to pay special attribute to and give thanks to a number of people and organizations and groups who have really been so instrumental in the success of the initiative. First, I want to point to our staff who have been absolutely amazing. I'm going to embarrass Kelly Fisher, the Executive Director of Science of Learning, who is right here in the front row, and Kristen Gagne, who is our Outreach and Evaluation Specialist, by their tremendous role in developing the vision of Science of Learning and in working to develop in great detail everything that we do in the Science of Learning, including the gazillion very specific things that need to be carried out in order to carry off a good, great symposium. There's also Mike Alexander, who you probably saw downstairs. He's been a devoted program coordinator, and we thank him very much for his role. Did I say Mike Alexander? Yes. I'd also like to thank the steering committee. We have a steering committee of 9 individuals from across the university, faculty members who have been absolutely dedicated to the science of learning, have worked very hard over the past 5 years, helping to develop the vision and helping to run the grants program, the fellowship program, and everything else you can imagine. the Oversight Committee of Deans. These are the deans from the 9 divisions of the university who have participated in discussing with us what our goals are, poking us very often to move forward in certain regards and to change direction in other regards. The university administration, who has been extremely supportive in our endeavor to develop science of learning. And as Sunil mentioned, most of all, our generous philanthropists who have understood from the beginning that science of learning is a vision. Realizing its goals does not require a quick fix, can't be done with a quick fix. Rather, it's a long game whose foundation is science that can give us fact-based knowledge, not alternative facts, but real facts that we need in order to guide action. So turning to today, rather than just basking in our accomplishments for the 5 years, we actually are going to challenge ourselves to go further. And hence the theme of the program, which I don't think that I have up here. We don't have the cover of the program up here, do we? That's okay. But the theme of the program, as you know from the cover of the booklet, is minding the gaps among levels of explanation. And what we're trying to do here is to present to you some conundrums, some difficulties, some challenges, some solutions in trying to fill the gaps between very different levels of explanation. Because if we want to understand learning at all levels of analysis, that's going to be a really hard job. Very often people are talking at one level and they're talking to people who are thinking at a different level of explanation. By level, I just mean different vocabularies, different senses of what a good question is, different senses of what the data mean, and so forth. And so we hope to highlight some of these big disparities and in sometimes some meeting of the minds between levels of explanation, and we hope to do that by organizing the talks in pairs to highlight these gaps between approaches, perspectives, and so forth, and help us move towards understanding what we would need in order to fill the gaps. So each pair of talks will occur with one talk followed by a 5-minute period of questions, the second talk followed by a period of 5 minutes of questions, and then there'll be a 20-minute question of broader discussion where people from the audience, of course, are invited to pose questions and challenges to both of the speakers and get perspective on the larger issues. I'm now going to turn the program over to Mike Miller, who is a member of the Science of Learning Steering Committee, professor of biomedical engineering, director of the Center for Imaging Sciences, and co-director of the Kavli Neuroscience Discovery Institute, and he will be introducing
Together, no false facts.
our first speaker, John Krakauer.
Well, it's a great honor. Barbara, congratulations. What a great event. I remember the first day when we were all together, the first event of this kind, I guess it was 4 or 5 years ago, in this room, and the room was packed as it is today. But I'm really happy because today I get to introduce 2 of my good friends and esteemed colleagues. And of course, John Krakauer and I have known each other since I came and he joined from Columbia. I'm going to keep my introduction short, but I'm honored to be introducing Dr. Krakauer today. Now I'm going to put my glasses on so that I can introduce him. John is the John C. Malone Professor at the Malone Center for Engineering in Healthcare. He's a professor of neurology and neuroscience. He's a professor of physical medicine and rehabilitation. He's a director of the Brain Learning, Animation, and Movement Lab. And he's the co-founder of the Kata Project at the Johns Hopkins University School of Medicine. I'm honored, John. I'm humbled. Dr. Krakauer uses physics modeling, psychophysics modeling, functional brain imaging, non-invasive brain stimulation, and studies in neurological patients to characterize the modular architecture of human motor control and human motor learning. We are all looking forward to his newest book, just released by MIT Press, Broken Movement, The Neurobiology of Motor Recovery After Stroke. Thank you, Dr. Krakauer. Good to see you, buddy.
Pointer. Okay. Oh, gosh. Thank you, Barbara. Thank you, Science of Learning, donors, Provost. I'm feeling very proud and multidisciplinary today. I rushed over from, I'm rounding and running the stroke unit in the neuro ICU over at the medical campus. And it's a bit of a change of pace, but I'll manage. I'm also really glad to be here, because I know why I'm really here, is that David Popple, who's the speaker after me, he and I plotted together about 4 years ago at a Gordon conference to write an article that came out exactly a year ago in Neuron, where we made a levels of explanation argument. And I don't know about David, but we weren't expecting the firestorm that this article actually caused. We only saw, of course, most of the time the positive responses. We were trolled, I'm sure, but we didn't get to see all of that. And Barbara, I think, enjoyed that article, and I think it was part of the inspiration for the talks we're giving today. And we do study motor skill and motor learning, so I have been funded by the Science of Learning Institute as well. And I will use it as an example for the point that David and I tried to make. And, you know, there is a concern. Yes, there are many levels of explanation, but we have argued in that piece and together that there is a kind of dominant reductionist bias in the study of the brain right now, and largely due to a kind of truly exciting increase in the tools available to us, but the tools, I think, are now wagging the conceptual dog, and we need to take a step back. That's what I'll talk about a little bit. And through my own mistakes, the example we've done in motor learning about how one can go astray and how one has to be more careful. Okay, so just to sort of make a plug for motor skill and motor learning, I'm sure everyone knows who that is up on the left, right? Please don't pretend you don't. I mean, someone call out his name, please. Okay, good. Who's that? Excellent. So that's Andrew Wiles, who solved Fermat's last theorem. Right? So isn't it interesting? And I actually, true story, got to play tennis with him when my brother was at the Institute for Advanced Study at Princeton. And I remember we were going to play doubles, and this rather frail-looking guy in whites and I think it was a wooden racket, maybe I'm making that up, wanted to be my doubles partner. I said, I'm not going to play with him, we'll lose. And David said, shut up, you solved Fermat's last theorem. Right? Anyway, it's interesting, is it not, that you knew who the basketball player was, but you didn't know who, arguably, the equivalent is in the intellectual space. So we, as a human species, are obsessed with motor skill. Right? 1 billion people watched the last World Cup final. 30 billion cumulatively watched the whole thing. But despite this overwhelming bias, we also have a kind of opposite bias, which is we kind of think that it's not the same to be good at sport as it is to be good at math, or good at music, or good at science. Right? So we're kind of conflicted between worshipping the motor system and motor skill and learning, and also thinking that there's something dumb jockey about it, which I'll talk about in a minute. Now, this is the piece that David and I wrote with our colleagues, Asif and Alex and Malcolm. And this is the one that I think sort of generated the debate. So, this is from Carl Cravis, a philosopher at the University of Washington in St. Louis. And he wrote a book about brain philosophy of understanding the brain, actually. And the way to think about this, and I hope I get the pointer here, is here you've got the mechanism in its totality at the top level at S, and here it is sighing, it's whatever it is you're trying to explain behaviorally. And then at the lower level, you have the components X, and each of their activities phi, and it's the interactions of the X's phiing that is the decomposed explanation for the total behavior S that is sighing. Okay? Now, if you were to ask somebody, let's say that this was cooking, and you wanted to understand why somebody's a good cook, you might say, well, they're good at reading recipes, they're good at salting, right? They're good at stirring. And that's really important because the explanatory level that you're using to explain why they're good at cooking or sighing is at the same level as the phenomenon itself. It's not likely that you're going to talk about that chef's working memory capacity, okay, or their selective spatial attention. You will be explaining here. Now, functionalism in the philosophy of science will suggest that there are emergent properties and means of explaining that exist at the higher level, and you don't have to go down to a lower one. And even neuroscientists who believe that the fundamental level that needs to be explained in neurons or networks themselves won't say they have to be particle physicists or chemists, because if they're going to argue down and the turtles go all the way down, we could say, well, if you think neurons are the fundamental unit, study atomic particles. And they don't have an argument, actually, to fight that. There's just this intuition that at the particular science that you've chosen, there's a fundamental level that stops and the turtles don't go all the way down. Now, the problem that I've had, and I think David and others have had, is that this kind of discussion doesn't get had in university departments because they're siloed. And you can get into trouble with the reductionist view, and you need what you really need in the argument we made is you want a functionalist view with a causal mechanistic backup. All right. Oops, sorry. What did I do? Okay, so here's an example, and I know that Jim Knierim's in the audience. So here are levels, right? So for example, here you've got a mouse in a water maze. You can look at it behaviorally. You can actually look at its hippocampus. You can actually look at the synaptic organization inside the hippocampus. We've blown up here. And then you can talk about ion channels. Now, you can work on ion channels. You can work on synaptic plasticity. You can do network models of the hippocampus, or you can just study the animal in its maze. But the idea that you can just forego all these three levels and just talk about ion channels, which was basically in the 1940s was called the covering law, that there were fundamental laws at the lowest level which could explain away the upper levels, has, to be fair, I think, fallen by the wayside. Most people don't have that physical law view of how to explain behavior. But there is this view that somehow you can work maybe at these two levels from the bottom up, and it's actually going to tell us something more insightful about understanding the behavior than actually studying the behavior itself. And the point I would like to make is I think that is wrong. So in our paper, this is not a new kind of argument. I mean, this is a sort of a revividus version of it. But David Marr, famously in his book Vision in 1982, talked about levels of explanation. There was a computational explanation. You know, what is the system trying to solve in the world? The algorithm, in other words, what are the system, what is the recipe, what is the menu of steps that you need to go through in order to solve that computational problem? And then there was the implementational level. How do you actually instantiate it in neural tissue? And the example he gave is this one. Here's the problem you have to solve. You have to fly. Here's the algorithmic solution. You have to flap your wings. And here's the implementation, feathers. Okay? Now, famously, he had this to say. Trying to understand perception by studying neurons is like trying to understand flight by only studying feathers. It cannot be done. Okay? Now, this is a extreme view, in a way, and he was a neuroscientist who very much initially did think that you could do it that way. Okay, now, we're not making the claim, as you'll see, that you can be purely, as the philosophers say, functionalist. Okay, but there is a bias when it comes to the study of behavior in neuroscience, that feathers are what we should be looking at most. And then what the people who study feathers will say is we always do a little bit of behavior, right, to get the feathers going, right? So don't be mean. We do feathers and behavior. You just do flying. Right? But no, I don't buy it. Okay, and I'll give you examples of that. So let's get back to this. So let's imagine how you're going to do science at all these levels, right? You can look at ion channels, you can look at neurons, you can look at circuits, and you can look at behavior. And you can throw your tools at these levels, all right? So let's give an example of a good friend of mine, Conrad Kerding, and his colleague, did neuroscience on a microprocessor. So this paper, which also caused a firestorm, that I got to see quite a lot during its proof stages, came out before ours, and we talked about it in our paper. And it's extremely interesting because you need to look at these levels from the behavior to the ion channels in the case of the hippocampus and spatial navigation, and now imagine the equivalent with a microprocessor. So here's the idea. Could a neuroscientist understand a microprocessor? Now, see again, just like we saw there, that you've got the behavior, which is playing 3 games, one of which was Donkey Kong and 2 others, right? So this is an old microprocessor and a video game. Here it is. And then you have the decomposition, just like I showed you, all the way from the transistors being collected together to make certain kinds of logical gates. Here are the logical gate primitives, and then you can add the gates into, for example, something that does adding, and then this is what's making up the overall microprocessor. All right, so very similar to going all the way down to the ion channel rather than the transistor that we saw there in the spatial map. Now, the idea was, let's do neuroscience. Let's knock transistors out, let's record, let's look at connectivity, let's throw the kitchen sink of modern neuroscience. And what is the goal? The goal is to reproduce this fetch, decode, execute algorithmic architecture of the microprocessor that any engineering student here at Hopkins or anyone else would verbalize to you if you asked them how a microprocessor works in the setting of this video game. All right? So what you're trying to do is to understand the microprocessor. Here's David Marr, basically level 2, algorithmic description of it. And can you get that back by doing neuroscience on neurons and networks on it? No. It was a total failure. All right? They did everything. Right? Now, there have been meetings across departments that I've actually been in of irate neuroscientists, right? You know, just saying, so here's what they said. So we want to see what kind of understanding would emerge from using a broad range of currently popular data analysis methods. And here's it in bold. The analysis cannot produce the hierarchical understanding of information processing that most students of electrical engineering obtain. Okay? Now, David Marr and others would not have been remotely surprised by this result. Okay? The fact that one had to go to this trouble to rediscover the point is a bit depressing, but nevertheless it's delicious as well. Right? So what happens as a substitute for that failure? Right? Because it's not as though the facts that are extracted by the neuroscientific techniques are not true. It's not even true that they're not interesting. The question is what are they explaining? Okay. What they are doing is making causal necessity and sufficiency claims, that if you knock out this part of the microprocessor, if you lose this kind of connectivity, you lose this, you lose that. But that set of necessity and sufficiency claims cannot be constructed into that algorithmic flow diagram. So what I argue, and David and the rest of us argued in the paper, was that there's a kind of psychological panic that this induces that one has to escape from. And how does one do that? Well, one does this. One does the science, which is perfectly fine, right? You do a manipulation, you manipulate a circuit to intervene on a behavior, and then you make necessity and sufficiency arguments. And then after you've done this kind of analysis, you make sentences of the claim of, you know, the circuit is the cause of the behavior. And then you go one step further and you say the circuit plus some filler verb, and you can take your pick here, right? They're all over the literature. Modulates, shapes, mediates, ensures, enables, plus that. No extra conceptual work of any kind has actually been done, right? But it's so not satisfying to have just made these necessity and sufficiency claims that all this verbiage just generates itself across all the papers in the field, because there's this lack, there's this little whimpering lack that we haven't actually explained the way that the engineer could explain the algorithmic circuit. And these are called filler terms. Right. Now let me give you an example. So Carl Deiseroth, who discovered optogenetics, who I was lucky enough to open a conference with in Germany late last year, went out to dinner, and I told him I was going to give him a diss, does this kind of work, right? Optogenetics allows, and it literally in a review article that he recently wrote, very beautifully well-written article, explaining how optogenetics can do beautiful work on necessity and sufficiency claims. But this is what you get, though. Understanding the neural mechanisms that mediate, there's a filler term, social reward has important societal and clinical implications. Hungdell found that the release of the neuropeptide increased pro-social behaviors, and then oxytocin release influenced social behavior. There's another filler term, right? So in other words, this is all true from a causal sense, but why oxytocin should make you more sociable isn't answered, right? You could put anything in there. You take your molecule of choice. You would have the same response to the sentence. So motor learning. So here's the classic experiment, behavioral experiment by Brenda Milner, who was in her 90s, and this was a patient, HM, who had intractable epilepsy, and in an attempt to control his epilepsy, he had a bilateral temporal lobectomy and had the hippocampus and other structures removed, and developed a profound anterograde plus some retrograde amnesia. And in a landmark experiment, so this is a patient, if you met HM, you would introduce yourself, you'd say hello, and then the same thing would happen the next day, and you'd have no familiarity, no sense of who you were. You'd have to go through the whole introduction again. So what Brenda Milner did was this incredible experiment where she made HM mirror draw. So basically, you see your hand through a mirror, vision of your arm is obscured, you have to trace the double perimeter of a star, and the quality of your performance is how long you can stay within the star, and you can do something called a root mean square error to calculate that. And amazingly, HM got better across days, but each time he was asked to do the task, he didn't even have familiarity, didn't know what he was being asked to do. So there was this incredible dissociation between a declarative, explicit awareness of what was needed, and yet was better at the task, even though did not know had done it on the previous days. Okay? So this was, you could argue, was one of the launches of the multiple memory systems view of cognitive neuroscience. Now, in the lab, you can not do mirrors and pencils and things like that. You can do it on the computer. And, we and others have spent a lot of time studying essentially the sister computer task to that original mirror drawing task. Now, it turns out, with an irony, which I don't have time to go into today, that the mirror drawing task is in some ways more than this, but that doesn't matter to the argument I'm going to make now. So you can basically have people reach with a mouse, for example, or with a detector towards a target on a screen, and you can basically dissociate what their hand is doing with the cursor and where the cursor actually goes, so you see this systematic error. It's a little bit like mirror drawing. And then you get better over time. Implicitly is the argument. You don't realize that your hand is now going off to the left and the cursor is now going into the target. You've adapted. This happens incrementally, trial by trial. Many, many animals can do this. You can then fit a function to this. You can have parameters that fit that function, and those parameters can be given meaning. So, for example, you can have a learning rate, and you can have a retention factor, and then you can sort of inscribe biological meaning to these parameters that you fit to the function, and then you can do imaging, and you can put in the design matrix of your imaging, the parameters on the fits, for example. And you can start looking for the neural basis of this behavior. Now, and this kind of learning, and the paper that we published way back now, is actually very implicit. In other words, when you first aim with your hand to a target, you go where it's expected. Oops, sorry. So this is the classic thing that I just told you. Your hand goes there, the cursor goes there, and then over time, you now aim your hand over here. We don't even realize it, and the cursor goes into the target, and there's a learning curve. This is your baseline behavior, and here's the learning curve. Interestingly, if you ask people to be cognitive about it, in other words, you say, don't bother with this old reptilian system, just aim directly to this target in the first trial and get rid of all this incremental learning. Sure enough, you can do that. So in other words, here are your first 2 errors. You're then instructed to cheat, and blam, in 1 trial, you're down to 0 error. But then something very spooky happens. Despite your cheating strategy, you get worse and worse and worse over time. It's very disturbing, right? But why is it that you're trying to hit the target and you're getting worse and worse, even though you're applying the same strategy that worked in the first trial? But all of you should see, and this is why we've plotted this way, that that learning curve that I called implicit looks very much like this learning curve that's getting into trouble after the initial application of the strategy. Now, what this turns out to be about is that despite the fact that you want to hit the target, you aimed the cursor somewhere else, and there's a part of your brain that wants the cursor to go where you aimed it and sees the error as a mistake and tries to correct that prediction error of where you aimed, despite that overriding your more strategic desire for the cursor to go into the target. You don't care where your hand is aiming. It's a very implicit sensory prediction error-based system. It overrides the experience. So in a kind of way, it's got an analogy to HM. There's a system that has remained and a system that has gone. And you know, you can do experiments to show that patients, is what we call in neurology paradoxical brain, can do some things after brain injury better than we can without brain injury. And sure enough, this is true, that patients with cerebellar lesions can in fact cheat better than we can on this task, and they don't show that implicit drift. Why? Because that part of the brain that we think is responsible for sensory prediction error learning has been damaged. All right. And I did exactly what I just criticized. You fit a function, you look at the parameters of that function in brain imaging, and you go, oh, look, these are the brain regions involved, fill a term, with this task. All right? So all looks good. HM, the adaptation task, a pure implicit system, there's the cerebellum and other areas of the brain. All is good. And it's so good that you end up with a mathematical framework. And it's interesting that our provost talked about Kalman filtering and Bayes rules. Well, sure enough, you can apply a Kalman filter model to this kind of learning. We've done that too. And then you can come up with a diagram, a level 1 and level 2 diagram of what's going on. Right? I don't have to go into this in detail. And then you can give it an anatomical framework. Cerebellum here, the forward model doing the predictions, the control policy coming out of motor cortex. It looks great. Consilience, mathematical model that makes sense, the parts of the brain that seem to map onto those computations, and the behavior. Right? Not so fast. Here's the problem. Is that if you, and I was lucky, I got to speak to Brenda Milner about this experiment, is what actually happened that day, or those days, right? In other words, when the patient came in and you had to go, okay, this is a mirror, this is a pencil, this is what you need to do, those are very verbal instructions, right? And then the next day, presumably, you had to go, this is a mirror, this is a pencil, this is what you have to do, right? So, just because HM couldn't remember using explicit verbal instructions across days doesn't mean that he didn't have to use the explicit verbal instructions on each day. So one of the big mistakes about this experiment is people think because you can't remember what you did, it doesn't mean that everything that you did was implicit on the day that you did it. Hope you can follow that. Right? And when I talked to Brenda Milner about this, she said, you know, it's interesting. We didn't quite record how much instruction we had to give per day. But clearly, I just want you to know that there's a very explicit component there all along. Right? And then we wrote, so Jason Stanley and I, a philosopher at Yale now, wrote this article about motor skill, and it was based on this article where we provoked people who thought that HM proved that motor learning was largely implicit because HM could do it, Motor skill depends on knowledge of facts. And actually, Barbara and others have done some really interesting work, I think, which kind of supports the view that we took here. And then we wrote this article, Is the Dumb Jock Really a Nerd? Right? Because, I was actually asked 2 years ago by Time magazine, they were writing an article about LeBron James, and they were very worried. They kept saying, Dr. Krakow, can we call LeBron James a genius? Because he's really, is it just his muscles or his big body? Right, and I said, of course you can call him a genius. And this was the argument we made in these two articles, based on the fact that there was a highly cognitive component hiding all along in that HM experiment, which has been taken as a launch for the idea that there are some things like motor skill that are implicit, and you shouldn't give them any cognitive credit. And it turns out that it's true, because of this experiment by Roy and Park, these are doodads that you don't recognize. They're strange objects that you have to be instructed how to learn, and you have to remember how to use them to know how to interact with them motorically. And it turns out that patients like HM can never learn how to use these tools, okay, which is exactly what you'd expect if real motor skills were a combination of the explicit and the implicit, and the explicit has to be remembered as well. And sure enough, as soon as you get to complex things, HM, but nevertheless, I think that because HM could mirror draw, HM could have learned how to play tennis. Right? Complete nonsense. So the point here being that even motor tasks, despite what neuroscience seemed to be telling us, are actually a combination of both, and then that leads to a paradox. Because if you now do the kind of tasks that we use in the lab to study learning across days, and I'm not going to go into all the details in the interest of time, but it turns out that even these simple tasks are made up of a combination of deliberate explicit aiming and this automatic implicit system that I told you about before, and the two of these systems add up together to give you the net learning. Okay? And you can look at the paper if you want to know more of the details, but basically the discovery was that you have a cooperation between explicit and implicit processes, even in simple tasks that look very much like the mirror tasks that HM did. All right? So, just so you follow the argument, all these tasks have an explicit bit and an implicit bit. You can remember something across days, presumably in HM because he'd lost declarative memory. He couldn't remember the explicit thing he did on each day the next day, so the only thing that could have transferred across days must have been the implicit bit. And that implicit bit is the one that's been propagated down to us as being the main driver of motor skill and motor learning. Right. But what I'm going to tell you is that when you study memory across days in these tasks that are like that mirror task, and again, I'm going to just give you the punchline because of time. This is done by David Hubbard, who did his PhD with us and is now postdoc at Yale, and Adrian Haith is co-director of the lab, and they're actually looking at data that I'm about to show you. And I'm going to skip the details. I'm going to give you the punchline, is that you can actually take these tasks and you can dissect the explicit and implicit components by limiting the amount of time people have to think about it. You can control their reaction times. So the reaction time can become the independent variable. So you can actually play around with how much learning can you do when you're not allowed to think about it explicitly, and how much learning can you do when you have to. And the fascinating implication of this experiment was that Adrian and David found that the implicit system, the system that ostensibly has to be surviving across days in HM, doesn't have any memory. Right? The system that ended up remembering across days in the healthy subjects was the explicit system. See the difference between this gray line and the red line? Okay? So you should immediately, if you're still following, there's a problem. Because we're claiming that HM was remembering across days because of the intactness of an implicit system that we can study in the lab, and yet that very same system has no memory when you study across days. So then you should all be asking yourselves, what on earth did HM not forget? Right? Now, it turns out, and again I'll give you the punchline, that it seems as though the explicit strategies that you employ can slowly automatize themselves and themselves become implicit. Okay? So it wasn't the implicit system that was there all along with its own memory. It was these explicit things you were doing that with practice, even across days, were beginning to automatize and take on the characteristics of the implicit. And that's just also in this paper here, this diagram here, and basically it's just showing you, and this is complicated, but all I'm going to say is that green line that hasn't budged from here to here is your implicit system, and that blue line that's gone up is your explicit one that has become implicit. Now, why am I telling you all this? Right? Because you're wondering, but why is he going through all this sophisticated behavioral analysis? That's what I want you to be going. Why is he going on? Why couldn't you have just pointed at some brain regions and be done with it? We preferred his old version. Right? Well, because what happens is that unless you do extremely careful, and may I say clever, behavioral dissection first, you're going to be led completely astray when you start looking at your neural data. Like I was. Right? Because in fact, the whole brain wants in on it. You can't say, hey, look, shut up everyone over here, cerebellum, do your thing. Right? It doesn't work that way, because there's presumably a cost function that we don't know about, where all the regions make differential weighted contributions to what's going on. So to finish, just want to say that paradoxically, if what I'm saying is true, then we're going to learn more about motor skill and motor learning by studying chess and math than we are the simple tasks that we do in the lab. Because all of these take 10 years to be good at. All these take an hour or so. So wouldn't it be ironic if, after what I just told you, that the system that ends up making HM good across days was the declarative system all along, right? It was cognitive from the get-go, and whatever process requires cognitive modules to be automatized, and the more complex the task, the more you have to learn to automatize, and you may need to automatize module by module, your backhand, your forehand, your serve, your strategies. Imagine, that's going to take you a long, long time, right? And that, in fact, there is no difference between learning how to play chess and learning how to play tennis. Right? And what happened is that the HM story and those simple lab tasks led us astray, and then we started looking at their neural basis. But it's very questionable to me whether their neural basis is going to tell us about the neural basis of the things that we ostensibly care about in the psychological world. So what I showed you, this is a figure again, and here's the big bias that I'm complaining about with David. And basically the argument is you need to have a theory first, then you need to do behavioral experiments to test algorithms, then you can get constraints and confirmation from the neural level, and then that might refine your level of understanding when it comes to 1 and 2. And my brother's the president of the Santa Fe Institute, which is where complexity is studied. And he and I have been wondering whether there's some kind of trade-off between the complexity of a system and the level of granularity where you need to say, can you understand it? And I wonder whether, when it comes that psychologists kind of got it right by accident, that psychological variables are the right level of granularity to understand complex phenomena. And when it comes to simple tasks like eye movements, the stretch reflex, the granularity can be lower down towards MAR level 3 because it's simpler and you can actually understand algorithmically at that lower level. There's isomorphism between the granularity at the level of the implementational level and the understanding. But once you start getting more complicated, you go upwards. And what David has told me, and he must be right because he's the president of the complexity place, is that there's always a level of coarse graining where you can begin to have that aha feeling of algorithmic understanding. But that level of coarse graining is probably going to go up as the behavior you're trying to explain gets more complex. Which means, if it's true, that any attempt to explain a behavior beyond causality by going into neurons and networks is doomed. All right. Thanks very much. Oh, and I want to put my science and learning slide, because thank you for funding, right? So there you are. All right, thank you very much. Oh, good. Yes? I want you to go. I knew that I went through all those, finished with those details. I could ask questions. Okay. I'm happy to answer questions. Wow. Anybody infuriated at all? What a failure. All right. Oh, yeah, yes.
So I'm wondering, started off saying there's a bias of bottom up to top down. So you started off saying there's a bias of bottom-up levels of
Yes.
explanation, and you ended with this, and maybe the second step helps too, but I'm wondering about situations, at least some situations, where the second step is absolutely necessary, where the top-down can go astray and you're not actually, the psychological variables that you're trying to explain can't exist based on what we know about the implementation.
Right. So I'm not being as purely functionalist as some people are in the philosophy field, and David Marr seemed to be when he said there was no point studying feathers, right? I absolutely, in that diagram, believe that you want to refine, constrain, update your computational and algorithmic theories. And don't be very clear, all I'm arguing is that behavioral work is the best way to test computational and algorithmic theories, right? Implementation level work is usually causal necessity sufficiency claims. That doesn't mean that one can't, once you come up with your behaviorally inspired computational algorithmic theories, then refine, update, correct by going into the brain itself. In the paper, we have a great section that David wrote about sound localization. Right? You know, the computational problem is where's the sound coming from? Then there are different potential algorithms that can be used, temporal or spatial, and then you go into the brain to break the tie in terms of how it's actually done. So we're not, but what I'm saying is if you look at a journal like Nature Neuroscience or Neuron, they're just totally saturated with circuit cracking work, right? Where, like the example I gave, where they basically just record and play and they just throw their methodological toolkit, and you're supposed to go, what a tour de force of technique. And in the end, it's just sentences with filler terms, right? I don't mind the causality claim. Or the causality, my other work depends on causality for recovery after brain injury, right? But what I can't stand, right, is this philosophical sophistry where after all that work, at the end, you go, is that it? That's your conclusion, that pathetic little sentence, which is basically a restatement of the result? Is that how conceptually empty the work is going to be? Right? That's what's annoying, right? But so, and all I'm saying is that you can enrich it by doing better behavioral work. And what I don't buy is the idea was we get that now. So at Genelia and other places, we've got amazing behavioral paradigms and we're doing the circuits simultaneously. Right? But I just don't think, with few exceptions, you can do it simultaneously. Right? But you're forced to because you can't get published, right? Unless you have a bit of meat that's been involved. A neuron's been touched somehow. And all I'm saying, I'm not against that work. I mean, I'm collaborating with people at Genelia. Right? I like that kind of work. What I can't stand is that scientists themselves seem to be so conceptually anemic about what it is. Murray Gell-Mann famously said once about British physicists, you know, they're very, very, very clever, but they're not very intelligent, right? Right? And I think what we're having is a huge tidal wave of cleverness and technique and engineering, right, which is all great, but the thoughtfulness is atrophying like the appendix. I don't know why. What else? Yes.
So I just wondered if you could clarify, maybe this will be something for the general discussion later on, but so you were preaching to the choir boy here for the first 3/4 of your talk. And then I started wondering where you were going at the latest. And the last statement you just made very strongly, right on. But I'm confused though about what you think about ultimately the ability for us to understand these complex behaviors, complex feats of cognition at the level of neural circuitry or not, whether it's just two levels that are so removed we'll never understand one in terms of the other, or whether it's just the order at which and the strategies at which to get to that understanding.
Yeah, okay, so yeah, exactly, they're both separate. So one is absolutely the order and the strategy, right? The other one is absolutely, there are wonderful examples where they come together beautifully, like David Robinson here at Johns Hopkins, where he basically showed beautiful isomorphism between his computational theory, the neural circuitry of the oculomotor circuit, and saccades, right? David Robinson himself wondered whether that beautiful click-like fit was going to work all the way up. Okay. Understanding and explanation are not the same thing, right? You can say, I've understood something, when really you haven't, right? So when is an understanding erroneous, and then explanation is there to correct your understanding? Now, what I would say is, it may well be that the psychology of humans is such that you need a level of granularity that may go up from the circuit to say, I've understood something. You know. What I worry about is that it may not be possible to have the David Robinson satisfactory feeling of understanding across levels once the circuitry and the behaviors become more complex. So in other words, I might be able to say to you in a few sentences, how does the oculomotor system make saccades? But if you said to me, John, tell me in a few sentences how an ant colony works, I'd have a hard time. Now, that doesn't mean that there aren't levels of description of ant colonies and bee colonies that I can transmit. It's just that it won't be about individual ants and individual bees. So I'm suspicious that we may not get the can we understand a behavior by a circuit that you will go, aha, yes. Right? You'll never have that satisfaction. But we will be able to tell you things and facts that are necessary for that behavior to happen. That's my worry, that we may just be there's only a piece of the parameter space of understanding where that Robinsonian click occurs, and everywhere else, maybe we can only do causality work at the low level and higher-grained explanatory work with psychological variables. Do you see what I'm saying? That's my concern, but I don't know if that's true. All right, thank you. Oh, yes. One more.
Well, thank you. You said that psychology has the right granularity of conceptualizations, or
It might. I'll just.
it might,
Yes, yes.
Well, that was my
It's a
where my
provocation
question
for the
was going
neuroscientists.
to get at. For example, psychologists often argue about specific concepts of constructs, like, for example, in working memory, or there are tons of discussions. So when they have it right, why would they disagree? Or
Why would they?
Why would they disagree? Or there can be concepts or theories that might just be purely wrong. How does that fit to your
Yes.
your theory?
So what people, that's a great question, because this is where some people will say that you need level 3 to go from what the philosophers call how possibly models to how actually models, right? So in other words, you could argue that when Hodgkin and Huxley came up with their equation to explain how the action potential propagated, that your aha moment was already satisfied, but it mattered it matters that sodium and potassium involved. You might say, I wouldn't care if it were two other atoms entirely. It'd still be the same math, right? So I would say that, of course, we're always going to agree, because there's always redundancy in the fits of our models, right? You know, there are mathematical models that will fit but you could have another model that's slightly tweaked that would fit better, and then you have that model comparison problem, right? And some people like to do model comparison. I think that's what's going on in arguments, a kind of fuzzy model comparison. Or you do a killer experiment so the psychologists disprove each other, right? So it's complicated, but I'm not sure that the answer always is going to be resolved by going down to the neural level. Sometimes it is. Yeah. Thank you very much.
Good morning. My name is Brenda Rapp. I'm a professor and chair in the Cognitive Science Department here. And it's really my pleasure this morning to introduce our second speaker, Professor David Popel. And I'll tell you a little bit about him and his research, just very broad overview. So David, after growing up mostly in Germany, came to the United States where he did his PhD, his undergrad, his PhD at MIT, postdoc at UC San Francisco, and then became a professor in linguistics and in biology at the University of Maryland. He currently is a professor at NYU in psychology and neurosciences, and he's also a director of the Max Planck Institute in Munich, and it's the Max Planck for the study of empirical aesthetics, which I find incredibly intriguing, and I don't know that he's going to be talking about that today, but at any rate, something to know about him. And David's focus of research interest has been on a very fundamental question, which is important for what's going on right here. So he's interested in understanding now that I'm speaking, all that I'm doing is I'm pushing air out of my mouth, and the air that I'm pushing out of my mouth is causing changes in air pressure all the way across this room. Those changes in air pressure are going into your ear, and somehow your brain is able to understand the words that I'm saying from these changes in air pressure that go into your ear and your brain processes. And so David's work has been focused on trying to understand what are the cognitive operations that take place in the brain that allow us and allow you right now to understand these changes in air pressure that are hitting your ears. So he studies both the cognitive level or the behavioral level, maybe, John, as you've been describing it. We could have a little discussion about why the word cognitive seems so absent from your presentation, but that'll be in the general discussion. He tries to understand the cognitive operations that are involved, and also the neural machinery that filler word supports those cognitive operations. And he does so with a wide variety of techniques. He does behavioral studies, he does neuroimaging. In neuroimaging, he uses MEG, fMRI, EEG, so a wide variety of approaches. He's written hundreds of papers. He's been recognized in a variety of different ways. For example, he's a fellow of the National Academy of Arts and Sciences. He has made many important contributions to our understanding of speech perception. One thing that he's well known for is his bringing from obscurity back into the light the role of the right hemisphere in speech processing. He is also more recently working on a really fascinating area. I don't know if you're going to talk about that today, which has to do with understanding how brain oscillations, the oscillations in brain activity, how they contribute or the role they play in speech comprehension. In all my contacts with David, listening to his talks, having informal conversations with him, he's always he has a knack for finding interesting questions, and he has a real aptitude for presenting them in accessible, provocative, and often entertaining ways. So I'm really looking forward to his talk, and I'm sure that we'll all enjoy it. So welcome, David.
Thank you, Brenda, for your ridiculously generous to be here. Since I have the podium, it's my turn to talk. And before we talk about work, let's talk about some other issues for a minute. For better or for worse, we live in interesting times, and I guess it's for worse. So just as a little reminder, before we talk about the fun and intellectually stimulating and more geeky things, I think we should remind ourselves that we're the people who have access to information. We're trained to evaluate information. So don't forget to actually think about something and do something. Right, so to remind you, Einstein had a good quote about this, which is, the world is a dangerous place, not because of those who do evil, but because of those who look on and do nothing. So if you're doing nothing, that's not enough. I mean, we're ostensibly the intellectuals who have access to evaluate things, so it's the responsibility of intellectuals to speak the truth and expose lies. It's actually the title of a book by Noam Chomsky. So that's my school marmish reminder before we start. On a lighter note, although I don't know if it's possible to have a lighter note, I'm going to talk about three things that are very much related to what John talked about. So John and I had to do rock, paper, scissors. Who got to go first and then got to talk about our paper, and so he won. So I have to talk about something else. So thanks a lot for that. And so I will talk about the problem in a kind of related way, structured in three sort of little sub-chunks. One I call the MAPS problem, which is related to the kind of implementational level of analysis. So localizing what do we do when we do cognitive neuroscience. One I call the, cleverly and confusingly the mapping problem, which is how do we map, establish linking hypotheses between different domains of experience, and that'll be the biggest chunk. And I'm going to talk about some, at least one experiment in perverse detail to give you this kind of work, but hopefully in a way that's clear to everyone. And then I'm going to talk about what we ended on in John's talk, namely the experimental granularity problem. That is, what are we actually trying to do? Are we doing more naturalistic experimentation? Should we have theories, hypotheses, and so that's the roadmap. So let's begin with this question. How naive are you willing to be? So I work on speech perception language processing, as Barbara said. How naive are you willing to be? Apparently in our field, really naive. So if you go to a vision talk, this is the picture you'll see, right? So this is from an old paper by Felleman and Van Essen. This is the visual system, the anatomy and all its links, okay? And nobody bats an eye. It's a really complicated system, makes good sense. Okay. Here's the auditory system, really complicated, right? So, by the way, this must have been done by somebody who works on the brainstem, because auditory cortex is just this little thing up here. So this person really enjoys the brainstem. And then you go to a language talk, even now, even like, let's say, last week, and then you get this. Like, really? So there's a Broca's region and a Wernicke's region, and then there's a cable. So, I mean, that seems wildly optimistic. And in the unforgettable words of the physicist Pauli, since we're quoting physicists today, it's not even wrong. So if you remember anything from my presentation, and you should remember only one thing, then it's this, that, this is just, this did a useful service, it's very important, but it's incorrect in many ways, okay? So why? What's wrong with this very simple model? Well, for starters, let's just look at kind of pure anatomic facts. So imaging has been useful in some ways, and it's moved us ahead. So for instance, take the famous Broca's area, which we should think of as Broca's region. Well, if you look at it, all the little colored blobs in a really tour de force experiment by Katrin Amons and colleagues from a few years ago, it's really like 10 regions, and that's, each region obviously has laminar organization. So do you really want to make a kind of monolithic functional claim about this much tissue? I mean, that's idiotic. I mean, nobody would do that in vision or in any other field, so that's just a bad idea. Similarly, the wire, there's a nice wire going from the back to the front. No, that's not really true. There's actually a huge spaghetti wiring diagram that's extremely complicated, which people are trying to work out. So that's not a good sort. And if you really look at sort of the whole map of things that are going on, if you look at recent review articles, the parts of the brain that are underpinning language processing in various ways look more like Europe in 1648. So extremely complicated, and basically the entire brain is implicated. And from my own work, I also know that it's the other side of the brain. It's not, you can't just be a left hemisphere imperialist. That's also wrong. Okay, so these are kind of maps, right? We make maps, and of course it's extremely useful because we have to figure out where we're looking. I mean, where are you going, and how are you trying to, parse the problem? And I've done some of that work myself. So, for instance, when you process speech, you want to recognize a word or two. I want to say, thank you, sir. Red chair. There's a lot of machinery involved. I mean, even something as elementary as recognizing a word and putting it together with another word requires a lot of different subroutines, so computational subroutines, and a lot of different brain areas in both hemispheres. So even something that's putatively, functionally banal has lots of different moving parts which we try to understand. And similar things hold for meaning, of course. Now, if you really want to go down the, let's throw big data at everything route, you end up with something like this from an influential paper by Jack Gallant's lab a couple of years ago. And this was actually the cover of Nature. So this is where all the words are in the brain, so apparently everywhere. So this is if you have a kind of orgy of data and do very sophisticated data analysis, you end up with this. Now, since you just heard John, you might ask yourself, who cares? I mean, what have I now, so this is an interesting kind of maps problem. I made a very complicated map, but have you understood anything and have you explained anything? And clearly, if you reflect on this for, let's say, 30 milliseconds, no. Right? I mean, it's a beautiful, I recommend the movies. They're a magnificent piece of art. I'm an empirical aesthetics professor, after all. They're aesthetically valuable, but they don't actually teach you anything. So what's the problem when we do this map stuff? The problem is that it's just an intermediate step. It's kind of part of our homework. That is to say, we do need to do this kind of cartography, as we do need to know, because it's in fact true that things are spatially organized, but it doesn't mean that that's sort of like the beginning of the inquiry, not the end. It's not an explanation. So first message, other than the classical model that you saw in a textbook for language is not correct, right? Remember that? That's on the quiz. The second point is, don't confuse localization with explanation. I mean, I'm as much of a toy-obsessed scientist as the next guy. I like all my big tools, but I too am misled by making these fantastic graphs and thinking, oh, I found this blob, and therefore it's involved, reflected, and so a list of filler terms that I've all used and continue to use. So you have to back off of that. So first message, be very careful about what an explanation is and what understanding is. So this is, we started this earlier on. So that's the maps problem. So simply taking the cool techniques we have in making maps is a reasonable intermediate part of the research program, but it surely can't be the end, and it's not an explanation of any kind. And I guess the slides didn't really was offended. Oh. Really offended. I haven't even started yet. It's going to get worse. So let's get to the more interesting problem. The real problem is, that's no worries, I don't care. I can talk without using pictures. So let's get to this issue, what I call the mapping problem. So that's actually a difficult problem, and that's the issue that John laid out earlier, which is how do we negotiate between levels of study, and what are different levels of explanation? So suppose I do the experiment that I go to the Society for Neuroscience, or the Deutsche Gesellschaft für Hirnforschung, or any of these kind of things, and I say, look, what do you think are the primitives of your field of study? So if you had to write down the parts list, literally what are the parts that you need to account for any of the phenomena you study, you're going to get concepts like dendrite, or oscillation, or synapse, or you name it. Right? So the sort of architecture of neuroscience, and there's very little debate about that. I mean, there's some debate, but people might say, we have a good sense of what the implementational level is in terms of its primitives. Now, if you do the same, so, and there's, we love that, that's all good. Now, do the same exercise for, let's say, the Linguistic Society of America, and say, well, what are actually the elements that you work with to account for any phenomenon in language processing? It's going to be really different, right? So it's going to be constant syllable, morpheme, small clause, concatenation, and so on. So now you have these lists. You have a parts list. Right. Right, so you have a parts list from, am I allowed to walk up to here because my mouth is connected to my feet, so, okay. Okay, so you have a parts list from the neurosciences, which, you can look up in any neuroscience textbook. You have a parts list that you can look up in a linguistics textbook, and there's, of course there's interesting debate about this is the right way to carve it up, but it's, it's productive, and this is sort of the level of analysis. And now what? I mean, how are these ostensibly related? Well, we haven't the vaguest idea, right? We don't know anything at all. So basically, we're done here. And we should stop and go to lunch. And that's actually a reasonable answer. So a reasonable way to proceed is simply to give up now and say, I want to study linguistic phenomena, so I'm going to stay at this level of analysis. And I want to study neuroscience, I'm going to stay with this. Nothing wrong with that. The question is, do we have, are we going to pursue the research program that these things are related? And so then how are we going to make these linking hypotheses? And what is their flavor? So the flavor of the current climate is what John discussed earlier, which is a kind of relentless, naive reductionism. As we assume, everything we do on the behavior or cognition, sorry, Brenda, side, we can debate the merits of the strategic use of terminology. So everything on the left side should be reduced to the terminology on the right side, right? So there should be just a mapping from the left to the right. That's the easiest because those are the more basic, smaller units. But that really doesn't work. And one example that we discuss, that he didn't have a chance to throw in, so I'll throw it in. This example that we discussed in our paper that is an example of why it doesn't work is the famous C. elegans. Right, so there you have a case where we really understand the structure of the worm extremely well. So C. elegans has 302 neurons, 7,000 connections. We know the genome, we know the entire wiring diagram, but we don't understand anything of how the damn worm does anything. So that's shameful, right? That's embarrassing. And you can actually have, and I have had, let's say, vigorous lunches with Corey Bargman, debating why don't we understand why the worm moves left or right, and because there's no interest in that level of analysis to actually formulate the questions in a more granular way. So that doesn't work. So how do we proceed? Well, we just have to, if we want to not keep these separate, if we want to try to find some linking hypotheses, we just have to sort of figure out how to do it. And I'm going to give you now one kind of experimental example of how I'm proceeding, just to show you how it's not successful, but it sort of tells you something. And what I want to conclude with in this section of the talk is to tell you, here's some neuroscience data that has implications for how we interpret the structure of the mind, which is what my title is about. So this was the kind of bloviating, mansplaining part. Now comes regular experimentation. So here's so we ready for that? We good? So far, so good? Okay, so now let's talk about some research. So the experiments are a bunch of people, but the two people who've played the principal role in this work are Nai Ding, who was a postdoc of mine and is now professor at Zhejiang University, and Lucia Meloni, who was at NYU, is now at Max Planck. So the problem is a simple problem that Brenda mentioned, is that as I'm talking, all you're getting is a physical vibration of the air in some kind of structured way, and you have to abstract from that information that's very complicated and weird and derive meaning from it. And the question is, how do you do that? And so I've worked for a long time on different aspects of this, and I want to give you one example of experiments that I think give us make a little bit of progress, or I hope they're wrong in an interesting way. So here's what happens when you, this is a sentence, cats and crocodiles don't play together, which is true. And this is what you learn when you take an intro class in linguistics or phonetics. So this is called a spectrogram. It has time on the x-axis and frequency on the y-axis. And then we learn to go through and say, oh, look at this little splotch here. That's, a burst of energy. And then there's some transitions here. And this is what automatic speech recognition does. It takes a signal like this, it goes through slice by slice, and tries to identify the information here, and it does an amazing job. Actually, automatic speech recognition in the last few years has gotten really impressive. It's quite something. It has nothing to do with the brain, by the way. It's not how the brain works, but it works well. Now, there's another part of the signal that you see this is what actually arrives at the ear. This is this waveform. It has these big bumps and valleys. These are sort of peaks in energy, and then it goes down, up and down, up and down. And it turns out, so it's called the envelope, because it's like the energy envelope across the signal. So it turns out, very usefully, and this has now been done for about 10 years or so, that your brain actually is incredibly sensitive to this particular variation in the signal and actually locks onto it. It phase locks really precisely to these energy fluctuations. Right? So here's just one example. So one line, the red line, is this envelope of the speech, so this up and down. And the other line is, in this case, from MEG data. You see how closely it tracks it. So it's like the brain waves are surfing on the speech waves. Now, so that's just an observation, right? That's just data that we see, and we can do it many times, and it's been done in many different experiments and different techniques. You have to ask yourself, who cares? Always a good question about one's experiment, who cares? So if you're tracking, if you're just bumping up and down on this envelope, does this do any work for you? So let's actually look at the envelope for a second cross-linguistically. Is there anything interesting here that we want to know about? So as it turns out, it's extremely regular. So this is what's called a modulation spectrum. So this is basically this envelope, this thing, this line going up and down, now characterized quantitatively and across languages. Is there anything actually regular in this thing? Like, should your brain care? Is it something useful? And it turns out that if you look at the frequency of change of this envelope, it's extremely regular, and it's very peaky across a whole bunch of languages. So here's whatever 9 languages, and different speaking styles. So with audiobooks and sentences and huge corpora and conversations. So whatever it is across languages, it's between 4 and 5 hertz. So the modulation of your thing is between 4 and 5 hertz, no matter what. Obviously, there's variation within a sentence and a little bit between speakers, but it's extremely regular. If that's not a peak, I don't know what is, right? So this is a peak. So that means that the rate that you hear is roughly modulated between 4 and 5 hertz. So then you think, have I seen this number before? As it turns out, that rate is exactly the mean, so the period of that is the mean duration of syllables across languages. So that's very useful. So it turns out if you actually go and surf these waves of the speech and your brain locks onto them, what you're getting for free is the typical modulation of speech as it's modulated by syllabic information. But that's cool because you need that to actually segment the thing. You need some kind of chunks or primitives. So there's a kind of more fancy physiological way to talk about this. But let me just point to one little thing. Speech comes in as this continuous waveform, right? This is the thing you see up here. It elicits activity in the afferent auditory system. So this is a spike train. So these are action potentials going bum, 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 right? And you see this is not structured in any way. Then this input interacts with brain oscillations, which are just part of the architecture. That's the breathing of the brain at different rates. And it turns out this interaction inserts the little white spaces that are not there. So why is speech more difficult than reading in some sense? Because in reading, I tell you where the white spaces are, and you know where to look. But speech doesn't have that luxury. You have to do that work by yourself. So the functional interpretation of getting onto these waves is the following. It's parsing the world into little acoustic chunks. So here's the sentence, "She had your dark suit in greasy wash water all year." I don't know, it's one of those standard sentences from a database. And this is what it looks like in a spectrogram, right? So it's time on the x-axis and frequency on the y-axis. And you can't, obviously there's no markers for words. You don't know where the words are, the phrases are, anything. And what this locking to the envelope does for you is that it actually segments the information into chunks. So it inserts the white spaces. So it's a algorithmic solution to to actually segment into usable intermediate things. So that's quite nifty, because you have to solve that problem, you know, whether you're a newborn or an adult or listening to a different language. So that's kind of cool. Now comes the, of course, say, well, okay, so the guy told me about how I can listen to syllables, but I'm not just interested in listening to ba, ba, blee, blah. You know, I'm actually trying to extract words, phrases, and meaning from this information. So is this trick somehow scale-upable to something that I'm more interested in? So this is now where the experiment, you know, gets more fun. So back to the signal itself. This is what you're sitting here, this is what you're getting to your ears. So the gray line is the waveform hitting your ear. The red line is the speech envelope. But of course, there are different levels of analysis. That is, I've been telling you about just the very surfacey level, the phonetic level, that has sort of a syllabic interpretation. And there's some correlation between these bumps and valleys and the segmentation into things like they went on vacation, right? So that's nice. That's a nice intermediate result. But what you're trying to understand are words like they went on vacation, and none of that information is actually in the signal. Therein lies the problem, right? So when you hear something, it doesn't come pre-labeled, like now comes the noun, now comes the verb, now comes the preposition. You have to do all that work by yourself. And then, of course, there's structural information, like information, like they went on vacation has a certain structure. This is how you interpret it, its meaning. Okay, so far so good? You get the general problem? So now can we scale up our little oscillations entrained to the signal thing? So this is how we're thinking about it. So ultimately, I'm interested in parsing linguistic structures, right? So continuous speech, and that has different levels of representation from sentences, phrases, words, syllables. So these are sort of non-technical ways to think about this. And what I just talked about right now is that the neural code for each linguistic unit must change at the rate of that unit, right? So if the syllables happen at a rate between 4 and 5 hertz across all languages, then the code dealing with that must be happening at that rate. That's, you know, a reasonable assumption. If that's, and we have neural oscillations that are sort of the breathing of the brain due to its excitability cycles. So that you get for free. That's off the shelf. And now the question is, does that scale up to these higher levels of analysis, right? So this is the question. We know the bottom. It's very well established for many years. Does it work for the top? Okay, here's how we tried to test that in this very peculiar experiment. So we make materials with different levels of abstraction. So remember, I just told you that the first thing we do from a brain's eye view is we create discrete units, right? So we segment something into discrete units. Now the question is, are they abstract? So here's how we do the experiment. This experiment we've done in, I'm going to show you results from Mandarin and English, but we've done it now in Hebrew and in German, French, Italian, so it's works across languages. So suppose I take a bunch of monosyllabic words. So this is, the Mandarin version. Here's an English. These are not glosses, by the way. So an example like dry fur, rub skin, new plans gave hope. Each syllable is carefully crafted to be exactly the same duration, 250 milliseconds, and I concatenate them so the thing happens at a fixed rate, right? So they just happen 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. There are no breaks. So there's a rate of the stimulus that's 4 hertz, completely regular. But then I fiddle around with them. So I record each individual item, so I can create higher order phrases, right? So 2 go together, so they're going to be at a different frequency. And if I put 4 of them together, I generate a sentence. So the stimulus itself will change at 4 hertz, the phrases will change at 2 hertz, and the sentence at 1 hertz, but none of this information is in the stimulus. You have to build that all by your lonesome, right? So let's see what happens. Or let's see, first of all, let's see how it sounds, because it's so weird. So this is what it sounds like in Mandarin. Oops. 拐弯青草发芽，飞机降落，游客爬山，母鸡下蛋，灯泡发光，英雄救火骏马奔驰，农民种菜。For example. Now, so you're lying in one of these machines. In this case, it's an MEG machine. It's like a giant hair dryer, which is superconducting quantum interference devices all around your head. And you measure the magnetic field, And this is now we're taking, since this is Mandarin materials, let's start with Mandarin speakers. So we take native Mandarin speakers, we stick them in, and we record their brain activity to see how they respond to this in the frequency domain. Since I just told you the syllables are happening at 4 hertz, the phrases at 2 hertz, and the sentences at 1 hertz. Let's see what happens. Here's what happens. This is the part where you go, wow. So unsurprised. So, and here's our little quasi-linguistic tree, right? So each of these grapes is one of the syllables, and they go together in two are paired for a phrase, and the whole thing is a sentence, and it happens continuously. So you get a big peak in brain activity at 4 hertz. It's exactly the syllable rate. That's not surprising. That's just a replication of what we did all along. That just shows that your brain tracks the envelope faithfully. Okay, that's a reality check. But then you see 2 big bumps, one at the rate of the phrase and one at the rate of the sentence. But now you have to ask yourself, where did they come from? They didn't come from the stimulus, from the signal, because it wasn't there. Nobody said, I'm a phrase, I'm a phrase, I'm a phrase. So you had to actually add that in. So that's a very nifty result based on neurophysiology. And now you have to ask yourself all the questions of reviewers. So let's go through reviewer number 1, reviewer number 2, and so on. So reviewer number 1. Well, maybe this is just some kind of interesting dynamical systems problem and you're seeing subharmonics. I want to see a list. What happens if you just mix them up and you can't put them into structured representations anymore? Good question. You present a list, right? So this is like eggs, butter, sugar, toilet paper, so there's no phrasal information. You still present it at the same rate, and you get a response at the correct rate, but you don't see a response for phrases or sentences. So it's not just some kind of physical property of the system. So, okay, reviewer number 1, go away. Easy. And while we're at it, reviewer number 1B, can you do it in just smaller chunks? So can you show that you follow smaller chunks? You can. So if I just put them together in little phrases like angry birds, dirty laundry, boring talk, then you get basically, you always get the frequency that goes with the stimulus. That's sort of your internal reality check, and then you can show that you actually track phrasal information, but not the sentential information. So that's a good sign. Then you can replicate the original experiment. Now let's go the other way around. Let's take English listeners from blue states and give them the Chinese materials, the red cherries. Now, they are obviously going to hear the stimulus, which is just 4 hertz modulated, and they're not going to get any of this because they don't understand Chinese as far as we can tell. And it's true. So the English listeners get a big peak, so they follow the physical signal, but they don't internally construct the representations necessary for decoding. Okay, good. Now let's replicate the thing for English, make sure that it works here's what it sounds like in English. So you're lying here in a machine for about an hour and a half listening to this, just to give you a feeling for the pain.
Poor friends paid bills, our boss wrote notes, drunk dudes sang hums, fun, games, waste time, kind words, warm hearts, tall guys, flea, camp, rude, cats, claw, dogs, quiet, lamb, ate, grass, wood, shelf, holds, cans, iced, beer, cost, cents, new plans, give, hope, large ants, built, nests.
So imagine doing that for a while. It's really, it's psychiatrically challenging. Okay. But it works quite nicely. Okay, so it works for Chinese, Mandarin, it works for English, so we're home free. So interim conclusion, cortical activity, or as the breathing of the brain, of these low-frequency neural oscillations, are entrained to sentential and phrasal information in the speech, but that wasn't there. So you had to bring that. Right? So your brain had to construct that on the fly. And because we did a lot of, this is a long, painful paper, don't read it. It's not confounded by acoustics, because these were actually individually made, flattened, and so on. So this is something really about you bringing it to the task. So your brain is constructing these grammatical structures. Now comes a real reviewer number 3 kind of questions. These were a little tougher. So as you know, the current flavor in psychology, computer science, and neuroscience is everything is about statistics. It's statistics all the way down. That is, it's corpus analysis of everything, and then you can predict and fit almost anything. So the question is what we're seeing in this kind of pattern of brain activity really structure building operations or abstraction? Or is it simply following a statistical model of the corpus statistics in your own head? That's a fair and irritating question, to say the least. So we built another experiment. This is this is even more painful. We brought people into the lab and taught them a fake little language for several hours, where the transition probability is held constant, right? So if you're just tracking transition probability, which is what the argument is, suppose I overload you with a particular transition probability, like in this case. So let me just play it for you, because this is now, really annoying.
John speaks Dutch. Her dad wrote a book. Her dad speaks French. Jess wrote a poem. Her dad didn't answer. A girl speaks Russian. The boy wrote a story. The boy didn't move. John didn't come. Her dad speaks English.
So a few days of that were really, well, NYU undergrads, whatever. It's expensive tuition. So if you're just if you're just tracking transition probability, you should be tracking, whatever is the transition probability of this, which is 1/5, should now show up in the response, overriding or at least influencing the structure building operation. Right? So let's see so it's a different prediction. The prediction is your brain response will look like something on the lower right. You're just tracking the transition probability and no longer the structure building operation. We did one more that's even funnier. So because, many reviewers, this one just I like playing because it's fun. These are completely predictable sentences. So once you know the first word, you know the rest of the sentence, if it works.
Dogs can be smart. My cat is so lovely. Amy owns a farm. Homework needs to be done. Nancy works at home. Rumors are not true. He will take the train. Matt married Carol. Earning money is hard. New York never sleeps.
And so on and so forth. Right, so for these kind of things, the participants come into the lab for several hours, they're exposed to this kind of nightmare, then they come in the second day, again, so numerous hours of learning this kind of stuff, and then you put them in the machine, and you measure their neurophysiological responses to this, and the question is, are they now tracking the transition probability, which we've artificially ramped up, or are they tracking the structural information, which is part of the kind of the syntactic information? And the answer is, of course, otherwise I wouldn't be here, they're tracking the syntactic information. Okay, so you can't override. So the response that you get from these looks just like the response from sentences that are novel to you each time. So of course you always track the stimulus rate, that makes sense, but you also build these intermediate phrasal representations and sentential representations, even though you have the entire chunk stored. So that's a nice and interesting challenge to a pure statistical explanation. Okay, now reviewer number 4. We're almost done. It has 5 reviewers. Reviewer number 4 says, but nobody speaks like that, which is true. I have an uncle, but nobody really speaks like that. We use short sentences, long sentences. So naturalistic speech is very different. So we had to do the experiment again. Then you have to use very different analytic techniques to make sure this scales up to a naturalistically structured speech, and it does. I'm not going to explain this to you because this is a bit more, this requires even a glance into the supplementary materials. But if you play, these are sentences of different lengths, many different lengths, short ones, long ones. And if you align them all, let's say at the big break here where the vertical line is the end of one sentence and the beginning of the next one. And you, of course, see right away that there's a kind of dynamics going back at least 5 or 6 syllables towards the end, and then a big onset to the beginning of the sentence. But you have to ask yourself, how do you know? And how do you know this is the beginning of a phrase? Well, you don't, right? Because it's not in the signal. You have to construct it. And in fact, if I give you naturalistic materials and I change the size of the constituent, so let's say 3-syllable noun phrases and 4-syllable noun phrases, I can manipulate these responses in systematic ways. So you must be tracking structural information, or what in linguistics is called the constituent structure. So that's cool and weird because it's abstract, very abstract. Okay, now last reviewer. The last reviewer said, this was even more annoying, I want to see you localize these responses in the brain because this is not interesting. This is just behavior and something weird about linguistics. Show me the brain. So we, to do this, conventional electrophysiological data aren't so straightforward to use for localization, so we had to use epilepsy patients, what's called electrocorticographic data. So this is where a few patients, in this case 5, we now I think have 7, have each dot is one of the electrodes that is part of a grid implanted in the patients for pre-surgical evaluation prior to epilepsy surgery. And we now record the same experiments like this. And here's the cool, so we follow the rules of the reviewers relentlessly. But something interesting comes out here. So now, what would you expect? So is there really a structure building operation that just builds these constituents and then ships them off for the next computing step, or are there many places where this might happen? And it turns out this is what you find. This is, I thought, was pretty neat. So here's this is now done in English, by the way, right? So these are English patients, English-speaking patients in the NYU epilepsy unit. So take a look at these down here, the red ones. These are electrodes where you get a response only to the phrasal information and to the sentential information, so the one, but not the stimulus itself. That is, those are electrodes that aren't particularly interested in what's happening at the surface, at the input rate, but they're really interested in these. And they're distributed in a bunch of different places in the posterior part of the temporal lobe, temporoparietal junction, some parts of the frontal cortex. So it's not a one-off location that does this kind of structure building, but it's actually it's a kind of computation that lives in a bunch of different areas, which I think is pretty interesting, and you can do it in many different places. Okay, conclusion of this one experiment. This is one experiment, but there's obviously many experiments. So what the takeaway is that the brain breathes in these low frequency rhythms, neural oscillations, and these slow rhythms can match the time scales of larger units, of linguistic units, even when they're not present in the input signal. So you can use those to actually build abstract structure, and that's what you're trying to do. And these tracking of these linguistic units is not based on statistical information, transitional probabilistic information, and it's not based on acoustic information. So what's the most likely explanation? Using Occam's broom, it's that you actually have internal rule or grammar-based, cognitive-based system or a set of computations that actually drive these things, which is, so where are we at the moment? You build discrete units, and the discrete units are abstract and interact with each other rule-based. That is the conclusion of the brain data so far. Okay, last point. So this is unpopular, and you can like this conclusion, but you would be wrong, because it's the right view. It's not popular with neuroscientists and engineers, that's for sure. But I have tenure, so. Okay, last point. So let me finish. What's the linking hypothesis? So where does this leave me? Well, the linking hypothesis is between a particular kind of neural oscillation and the physics of the signal, right? So the modulation spectrum, so that speech is modulated in surprisingly regular ways across languages. That's physics. The neurophysiology directly linked to that is the neuroscience, right? So these oscillations, building onto that, and the fact that this links directly to syllabic duration and segmentation, that's the linguistics part. So I have a nice link between what you need to decode in linguistics, what the mechanism is neurophysiologically, and what the physical signal is that conditions it. So that's a very kind of rich research program to pursue. Okay, last point now about the experimental granularity problem. So again, this goes back to John's talk. It goes without saying, or I think it goes without saying, that what we're all interested in is sort of, how we work in real life. I mean, how do we work sitting at a kind of divey bar in Baltimore and walking in San Francisco or something like that? I mean, and that requires, complicated aspects of so the world is multisensory, it's highly contextually dependent, it's interactive, and of course that's what we're trying to do, right? So we want to have a kind of understanding of how we work in a naturalistic way, and the kind of stuff that moves us, that we really get excited about, are, let's say, things that make you immediately reflexively emotional, or that are super cute. I have cat videos too, here. Socially interactive. And so these are actually the most frequent pictures in Google. The most frequent one is not rated PG. I can't show you that. or awesome. These are the kind of things we want to understand, things that are, in a social context, exciting. And I'm on board with that. I would like to understand how emotion works and why things, why I think my dog is cute. But the fact of the matter is our understanding hasn't come from that. Our understanding has come from very different kind of experiments, such as this kind of thing, right? So this is just to learn something about contrast. So that's neither cute nor socially interactive nor awesome. It's just a carefully constructed stimulus to understand something about the decomposition of the problem. Or color, right? So this is a kind of Mondrian-inspired picture by Edwin Land in experiments on color vision, the Retinix theory which he developed. Or the famous Gabor patch. I mean, if I'm in another experiment as a subject using Gabor patches, I'll shoot myself. But many, many things have been learned using Gabor patches, which are also not particularly cool. Or visual motion is learned using, the random dot patterns that move around. So the models we've constructed have been pretty successful in terms of what we're trying to distinguish, between causal mechanism and understanding. Build on these kind of careful decompositions, and rich psychophysical research programs have been going on for 100 years. And so they make reference to concepts like, similarity space or Gabor filtering and things like that. They don't make reference to emotional or awesomeness and cute. And so the issue is, how do we balance between our desire to get to the rich, socially interactive things that we care about, but this kind of granularity that's theoretically well-motivated, computationally explicit, and also realistic in terms of neuroscience. And that's quite difficult. And the right paper to read about it is this one. This tells you, this is the, run, don't walk, to the library to download this, or do it right now. Because at least it thematizes the challenge of doing this in a meaningful way. Okay, so what's the conclusion? Making maps is not an explanation. It's an intermediate part of the homework problem. It's a really good and important problem, but localization is not explanation. I fall into this trap every time I read the New York Times, because there's always a picture with a brain. And it says love or free will or God or whatever. But it's just not. Second, the mapping problem is the really serious problem here, which is how across levels of study do we find linking hypotheses that ultimately allow what understanding is, and what do you think an explanation is? Very difficult. The world is a complicated place, but we still need to be what I call radical decompositionalists to generate explanatory understanding. So we want context, but we won't get around what did we call it? Like carefully designed, behavioral experiments that really parse apart the nature of the problem and give you new things. So my resolution for this new year is that we have good spatial resolution and we have appropriate temporal resolution, but we really need better conceptual resolution. And that's all I have to say today. Thank you for staying. Yes?
So, in part one, never met. I'm John. I love your work, David.
Hi, John.
I follow it closely. In part one, I felt like you were preaching to the choir, as far as I'm concerned. And then in part two, I felt like either you meant to tell the choir to go home and you were going to replace it with like a fancy sound system, or there was like a wink that I missed where it was going to be, hey, this is how we convince neuroscientists, but don't worry, relax. So you'll tell me which one it is. But in part two, I guess there's a number of ways one could ask the question, but in what sense, the data's all really cool, but in what sense is what we saw, I think you used the term structure building operations, or structure building as opposed to just structure reflecting. Another way to ask the question is...
Yeah, that's just on that particular point, you're absolutely right. I mean, it could be, we just measure some output of a series of underlying computations. So when you see a peak like that, that's not, that's an index of something that's happened in building what I take to be a pretty abstract structure. So you can call it structure reflecting, that's fine.
Right, so in that sense, at the end, you also said something along the lines of, this is the right answer, but the neuroscientists and engineers don't like it. But didn't we know that was the right answer? Since at least like Chomsky's review of verbal behavior and, even before that, in the sense of you're saying, look, there's the signal doesn't, in its raw form, have a lot of information, but the information has to be there, and there have to be computations that are able to break it down.
But I am just, we must not hang out with the same people, because in my own lab, or I hired the wrong people. In my own lab, I have postdocs who come, let's say from engineering particularly, who are deeply unhappy with a conclusion that's not based on, let's say, a mapping to the surface or the episodic feature-based information of the surface stimulus. That is to say, look, this is why we do the experiments with, for instance, statistically controlling the materials or manipulating them.
Right.
Because the standard view and the most popular view is you don't need abstract structure. Right, I agree, and I think this is old news to me. I don't particularly need to be convinced that we have constituent structure, but I assure you that, let's say, my colleague Tony Movshan does need to be convinced that there's constituent structure, even though there's 100 years or actually 2,000 years of evidence for that kind of concept. And the idea is, why should I care about that kind of concept? Because probably I have a reductive thing to do away with it. And the fact that we need it to actually build internal representation is just dismissed as unnecessary. So I think, I do think it's the right conclusion, but I don't think that everybody believes it. I think, in fact, very few people do. I think if we polled people here, people who come from engineering or computer science, they would rather see an explanation based on statistical contingencies and surface features, and like, let's say, acoustic variation in the signal, because we can measure it and we can manipulate it. I just think it's wrong.
Yeah, I feel you, David. So it was a wink to the choir. I'm with you.
Yeah.
Yeah, thanks.
Yeah, there's in the back left.
Hi, Joe Ganem. Let me be reviewer number 6 here. Do those lower frequency syntactic signals attenuate if the subject loses mental focus? Or
yes.
They do?
Yeah, you can actually, Ilana Zion-Golumbich, a former postdoc of mine, has done a bunch of experiments on this and doing it at different levels of vigilance, seeing if they go away in sleep and that kind of stuff. So yes, they require not specific attention to something like structure building, but you have to be awake and able to process language in a canonical way.
Focusing on it, so you could actually measure mental focus.
So you can do more than that. So the experiments that Ilana has recently completed are using, for instance, the cocktail party thing. So suppose you have 2 speakers concurrently, and you slightly offset the frequencies, right, so that their rates are a little bit different. You can say, okay, look, please listen to speaker A, then you will track A. And listen to speaker B, then you will track, the frequencies will shift to track speaker B. So you can actually use this. For us, this is largely a kind of methodological trick to use something like it. But yes, you can track it quite carefully. That's right. Paul.
Paul Smolensky, Johns Hopkins Cog Sci. So I'm wondering whether the problem that you are up against really is about abstraction, as opposed to intuition. So suppose we repeat your talk with vision instead of language. We show there are evidence of neural responses to objects, to scenes, to types of scenes. These are very abstract things, but they are also part of our intuitive understanding of the world. And so do you get the same kind of resistance to those abstractions? And if not, is it really about abstractness?
I think you do actually get the same in the computation. I'm not a computational vision person, but I think that the degree to which people agree on levels of abstraction and links between surface-based features of visual objects and abstract interpretations that are independent of features. Let's say something as simple as viewer-independent recognition. That's a very high degree of abstraction where you need to be entertaining something at the surface and yet dealing with an interpretation that's very abstract, which allows you variability at the surface. I think it is about abstraction, and abstraction related across levels.
I just didn't think that was controversial in the same way. that higher
Again,
level
I mean,
abstractions
you are not the same reviewer. You're not dealing with the same. I think people in neuroscience and even in psychology are really resistant to this notion, and surprisingly so, even though I think there's hardly any counter evidence. I mean, it's a sort of, there was one more question, a little bit, yes, right there.
I'm Diana Gross. I'm with Johns Hopkins University, and I'm working, I guess, that third objective of the Institute that Barbara spoke about, and connecting the science to practice.
Yeah.
And I'm at a very beginning stage of it. And I'm finding your research fascinating. I work on educational equity gaps and with literacy. If you're studying, if your subjects were NYU undergrads, are they coming in with a better understanding of the linguistic, of the grammar, syntax, and all this? Does that affect your research and what you're finding, opposed to if the subjects came from a lower educational background?
It's a good question. I mean, and the answer is no. This is actually tacit knowledge. I mean, what you're tapping here is tacit knowledge that you get for free for everyone. It's going to be independent of that. I mean, it's sort of a very basic, I mean, barring gross pathology, every speaker from 4 years old or even younger has access to this kind of cognitive machinery and set of computations that do this. So it's sort of, that is actually largely independent of that. There may be other things. So for instance, the person next to you was asking about attention and things like that. They may be differentially regulated as a function of that, but the basic building blocks, building constituent structures and using them to decode information is sort of independent of that. It's really a architectural feature of the operating system, independent of it. But in terms of using this kind of machinery to put it into a school, I mean, I have done experiments where we measure an entire school class at the same time for an entire semester. I mean, I can share those papers with you, but there you can see how you can use some of the tools of your recording brain activity concurrently, for instance, to different teaching styles, and try to figure out what it means to be synchronous, engaged. How this kind of brain activity reflects what a kid is doing there. So that's more applied in that sense.
May I just ask that last mapping that you did, where you say let's look at the regions of the brain?
Yeah.
Can we effectively use that working with educators on how do we stimulate that area if we're trying to reduce gaps?
I think that's a question maybe left for the general discussion. I think that's a very controversial, but it's a good one. It's a good lead-in maybe to the general discussion, because I think people will have different feelings about that. It's a very interesting point. Yeah. Thank you very much. What happens now?
We're going to open it up. So we're just going to move into just a broader question period. So we have both of our speakers here, so you can ask either of them questions about their work, and also you can ask, questions that cross-cut across the two of them, across their two talks. Let me just throw out there a couple of questions that they came with.
Maybe John could answer that question.
Yeah.
That was just, he's in the role.
Let me just throw out a couple of questions that the speakers themselves, proposed for general discussion, but there's no reason to stick to these, but let me just put them out there so you can ponder them as you raise whatever questions you have. So it's open to all questions, but let me just put out these couple of questions that they proposed. John suggested that we might want to think about in this context, what does understanding mean? Okay, think about that a little bit. And David thought it would be interesting to think about how can neural data adjudicate between alternative theories of behavior / cognition. So again, just against that backdrop, if you have something related to these questions, it's great. Any other question you might have, now's the time. Ask these two.
Are you moderating?
I guess I will, yeah. So Patricia. Yep. Oh, the mic. I can speak very loudly. I'm Patricia Janik.
I think it's.
No, we need a mic.
I think for the recording, they need a mic.
Thank you. Thank you for those really stimulating talks. I'm Patricia Janik. I really enjoyed them, and I think in general, what you say will resonate with very, very many people, including neuroscientists, at least some of them, and psychologists. But I had a question that I want to direct first to, maybe to both of you. So within the first talk, we heard the question, why? And when you were talking about a very reductionist experiment, and that learning about oxytocin and social reward, you're still left with why. Does that play a role? Is it not? Oh, there we go. Hello?
Now it is.
Okay. Sure, sure. So John asked in the beginning the very critical question, why? Why does oxytocin, for example, impact reward? And so what I'm interested in knowing from you both is what is a satisfactory answer to the question why for you? So John, we, for example, heard about your really cool experiments looking at explicit and implicit memory mechanisms in motor learning. And at the end of that, I was wondering, did we get, or did you get the answer to why from those series of experiments? What is your why and what is the answer to your why? Does that make sense?
Yeah.
Okay.
Oh, this is on. Right, right. So yeah.
Do you want to move just a little more?
Yes.
So you're not like in a corner. I mean, I don't want you to feel that you're in a corner. I'll go in the corner. You guys take it.
Right. So that is. So if you look at how do we explain things, right? You go to physics. You know, this billiard ball pushes against that billiard ball, and it makes that billiard ball move. Right. It's all about sort of action verbs and consequences, right? And you look at Descartes' bizarre drawings where he would go down a level and just show things jostling that were causing the big thing, right? So it's actually a very deep question about what does it mean when some object through an activity impinges on another object, and you go, oh, I know why that billiard ball went, because another billiard ball hit it, right? And then you go to neuroscience and you talk about David Robinson's explanation of a saccade, right, where he says you need to have a burst phase and a hold phase. Reza Shadmi has written a beautiful set of reviews about this recently, right? And then you go, well, computationally, you're going to have to sort of integrate the velocity signal to get a position signal. And then you go, well, what neurons are going to have to be able to have that kind of computation? And then you get the whole thing, as I said in my talk. And you go, I understand how a saccade is formed, right? That feels a little bit like billiard balls hitting other billiard balls. Right? Saying that oxytocin is involved in reward isn't remotely close to that type of explanation, right? So if you want that kind of billiard ball, this hits that kind of explanation, I think it's really difficult, as I said to Jim, once you start getting up to more complex behaviors. But then you get what David was talking about, where you say, well, you know, I know that there's this grammatical structure in the world, and there's a problem. You need to put, as you said, the white spaces in all the right places, all the way up the level of abstraction, from syllables to full sentences. And then you begin to get the brain work, in my view, sort of beginning to confirm that that is the way the problem is seen by the brain, and it seems to be decomposing the problem in the way that one posited it would have to. Right? Now that you're right that is not, well, how does it take that abstract knowledge and impose it upon its oscillations so that it passes, right? That implementational level, I don't think David claimed that he knows how that abstract information is used, right? But nevertheless, at some level of higher granularity, beyond the implementational level, you can still nod, and we all nodded when he said it, because we were getting it, right? But my worry is that when we say oxytocin causes reward, at no level are we getting anything other than making a causal claim, right? So it's not understanding sentences at the higher level, like David gave. It's not understandings at the lower level that David Robinson gave. It's just a causal statement. That's my concern.
Oh, sorry. You have a microphone and then over here.
Hi, I'm Robinson. I'm a librarian here, and so I'm kind of an outsider, although I do work with both Brenda and Barbara when their literature needs. So all the recent talk about reproducibility, especially in psychology, and the problems you've both pointed out this morning with working at different levels and trying to talk across these gaps and what really happened with HM and all of this stuff. Now I'm curious about how can we better improve the graduate level of education in neuroscience and linguistics so that some of the filter words and those kinds of assumptions, causality, is all a little more clear to everybody.
My turn? I mean, it's a good question. Why I guess...
Come out here.
I want to hide.
I
have a mic.
He's wearing a mic.
I'm wearing a microphone still. I mean, I guess I would hope, or I encourage certainly my graduate students to not. So one of the things we do in graduate school is we throw them into these, technical extravaganzas that we use, and people have to become very proficient in all kinds of difficult to master techniques. And what we forget, and I think both of us sort of emphasize that, is kind of the hard conceptual work that goes into this, into the experiments, regardless of whatever level they at, into what even is an explanation. I don't know, when have you been to a lab meeting, in any lab, where, unless it's a lab that happens to work on the concept of explanation, we say, what does it mean for us to understand something, to explain something, what is the notion of a mechanism, and so on. So so a little bit more reflection would be good for graduate students, and maybe a course, quite frankly, in the history of science. So a semester of history of science hasn't hurt anyone. And it sort of forces you to face down some of these things. It's very useful. Philosophy of science, history of science.
Yeah, I would add, my brother and I just did a current biology interview on this topic. And you said you were in the humanities?
I'm in the library.
Okay, great. Okay. It turns out that books and essays, in my view, are, people have written about them, more complex objects than scientific papers and talks, right? And in science, we don't write books or write essays anymore, right? We write these salami slices of incomprehensible figures and things, right? What I think has to happen, I absolutely agree with David, people should be taught the history, the philosophy, the sociology of science. Okay? Any scientist who says they don't need to do philosophy should be immediately banished from a university. Okay? Because they're doing philosophy all the time, they're just doing it weakly. Right? Because they're constantly making normative judgments. Whenever a scientist says, this is an excellent, interesting paper, they're making normative judgments. There's no excellent variable anywhere plotted in the paper. So if you immediately say to a scientist, why is this an important paper, they're doing philosophy. Okay. The other thing I would say is, don't just do something, stand there. I don't know how many, if a grad student or a postdoc were to say to their PI, I think this week I'm going to go to the library and read. Good luck. Right? Good luck. When in fact, that's exactly what they should be encouraged to do. So unfortunately, what's happened is that there's very little discussion. There's an absolute worship of methodology and statistical significance. If Darwin were to apply for a job today, and they said, what do you want to do, Mr. Darwin? I think, well, I'd like to go on a boat ride for a couple of years, read Humboldt, and walk through forests with a notebook. Thank you very much. Do you do optogenetics? Right? What's happened is that academic science has become profoundly anti-intellectual. And libraries, I think, are the answer, because people need to read books again. Very, 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 very few scientists read books.
Your book, maybe. So. Just a pick one at random.
Hi, can you hear me? Yeah. My name is Sai Prakash, and I'm a former lecturer in the chemical engineering department. I have a question regarding speech production. I'm not sure if you're willing to answer.
Let's see. I might say no.
But that can come in second. And the first question I want to ask is, what is the impact of fear on learning. This I ask specifically because although I spent some time teaching here, I grew up in India, and there was a different teaching style and things like that. During a particular transition between one school to another, I noticed there were completely different teaching styles, and that had a significant impact not only on my development with regard to certain aspects, some positive, some not so. But I just wanted to know what it does. Actually, I mean, like to give you a broader picture. It went from a coeducation school with female teachers to a strict all-boys school with very strict male teachers. And I was wondering what the impact of fear is on learning. I know that people use the idea that some amount of anxiety in students is good for motivation because you don't want them to be too relaxed or too lax or not anything, but too much of it is detrimental.
I suspect there's somebody here in the audience who's better suited than us, right? I mean, there's certainly an interesting, extremely tight relationship between fear circuitry and learning. But who volunteers to answer this question? Who actually works on this topic here? Because it's not John and it's not me. Because it's a very good question, which is studied by people like Joe Ledoux and Liz Phelps and people like that.
I agree that there's. I would just say one thing about the teaching styles about fear. I mean, fear. I agree with David. I don't do fear, right? But I would say that word is used to diminish actual debate in scientific forums. If you go nowadays, people go, what a great talk, right? That's the first thing people say, right? Great talk, and then it's sort of like, what is it, the Oreo cookie thing? You have to say something nice, and you say something critical, something nice, right? And what's happened, I think, is because of this notion of fear, that you can't have debates anymore, right? Because any disagreement somehow now becomes internalized as an attack or ad hominem. Right? So fear itself is, and in motor learning there's work on punishment versus reward for learning rates, for example. But I think what my guess is, when you're talking about teaching styles, I mean, fear is unacceptable, right? Making someone frightened, I can't imagine how that could possibly be justified, right? But debate, I think, has been turned into this notion of it being criticism and attack, and that I think is very bad.
I have a 30-second answer to go into, just for fun, just as a shameless advertisement for my own research. This highly recommended paper about the fear circuitry as it gets turned on by listening to screams. And how are screams organized, acoustically? What do they lead to behaviorally? And what do they do when in terms of its activation pattern? It's a paper in Current Biology by Mylan. It's all about how when you listen to screams, the scarier you rate them, the more the fear circuitry is actually activated. So that's production and fear together. So I answered two of your questions and did advertisement. So score.
Just a couple more questions. So,
Okay, so Amy Shelton, Johns Hopkins. So coming from cognitive neuroscience and psychology and education, so short answer to the fear thing is there's not a lot of work on that. There's a lot of work on aggressive environments. And also I'll be speaking later today about making some of these connections from the levels of explanation into the education world. So we'll have a chance to hopefully talk about more of those things. And in thinking about what you, both of you talked about, where you really laid out frameworks for thinking about crossing these levels of explanation. And one question I had was how to think about the issues of development in these contexts, because really there's a huge disconnect between what we call developmental neuroscience and what we call sort of developmental psychology, developmental science at that cognitive level. So I was really curious in how you might think about those developmental issues in this space as well.
You know,
That's yours.
it's really interesting that, you know, people always say that when kids learn better than adults in motor skills, right? I mean, and yet when you look at the literature to find evidence that that's actually true, you can't find it. In fact, on the tasks that are used, the adults always do better than the kids. And then you're left with a paradox again, is, well, why do we all believe that there's a difference that you need to learn when you're young? Right? And I don't know the answer yet, although I have some ideas about why that is. And I think that kind of work would be really useful to, in fact, test our hypotheses that we use in adults or young adults. And I agree with you also that, you know, having spent a lot of time around developmental neuroscientists, that it has absolutely nothing to do. I mean, the gap, I don't think, could be wider than... with one incredible little paper, if I may advertise, there was a paper done in Science last year where they took mice that don't have a monosynaptic connection to their pores. In other words, mice don't have those monosynaptic connections, and they developmentally interfered with that monosynaptic connection, and postdoc in the lab showed. And then these mice were unbelievably dexterous. They were holding spaghetti going like this, and it made you wonder, why didn't they get selected for these super dexterous mice and lose those connections? So I think that was the one example where a developmental study was actually very profoundly interesting.
Yeah. Hi. Marianne Wilson, Kennedy Krieger Institute. I guess this is really a question related to the prior question. It's for David. Have you looked at developing, you know, over language development in children, say when they're at the single word phase, when they're building a vocabulary? Would you expect to see the syllabic response and maybe the phrase response developing there, and then later see development of that 1 Hertz sentence response?
Absolutely, very good question. Is being done by people, and yes, you would expect from, in fact, we can show from the get-go, even neonates, that you track energy fluctuations in materials very faithfully. So that's there from the get-go. But you would expect over development that, yeah, the peaks that are reflective, Fillerbird, of building structure building operations or things like constituency would come in later. And in fact, you can do it in the adult version. You can teach people artificial grammars. I just finished an experiment like that with Melissa Newport, and you can see at the beginning when you don't know the structure of the thing, you just follow the stimulus, and as you actually learn the structure, these peaks appear. Relatively quickly, by the way. You don't need a lot of exposure. You stipulate structure very early on in the learning process. So it's a very good idea, and it would be a very interesting non-invasive way to track when when a kid actually begins to have access to that, or when those kind of operations manifest themselves. So it's a good experiment there.
Hi, I'm Lisa. I'm a physics student here, so I'm kind of closer to all the engineers you've been talking about. I have a question for John. So what you say about the granularity of, you know, when you try to study a psychological problem, that speaks to me on a very deep level, because it's the same in physics. You don't always want to go to quantum mechanics to study a problem of a brick falling from the sky. But whenever you separate a system into its constituent parts, for each part, you could then also separate it and study that from its constituent parts. So in your field, do you think, well, essentially, if you do that, you will reach the neuron level. Do you think that would teach you anything new, or should you just stay on this granular level that you begin with? Because splitting it further won't actually produce any new results.
Well, right, that is the million-dollar question, right? In other words, no, it is. In other words, if you look at people who study complexity, there's no a priori way of knowing what the level of granularity should be, right? There's no formula, right? And then that's wedded with the question you asked, which is there some foundational level that is obvious? In other words, is the neuron the obvious place, or now the new worshipped thing, the circuit, right? There's no obvious way to know that's the right turtle, right? Neuroscientists think it's the right turtle, right? But it's not clear that it is, right? And then, as we argue in the paper, I think the reason why multi-level is good is that if you do have your favorite level of granularity, and maybe that'll just turn out to be taste, right? It does, that level you like will be enriched by going above it and below it. I really believe that. So even if you say that's your level of explanation, it will be enriched. And then the final point, which I think is the one that we should all solve, and it's the one, you know, at the Santa Fe Institute, for example, they worry about all the time, is we don't have bridging theories, right? I mean, the linking theories that David talked about. We can say it, we can intuit the need for it, we can articulate it every way we want, but an actual theory that does it is extremely difficult. Right? It doesn't exist in biology as far as I know.
Hey, I'm Hassan from Reza Shadmir Lab, PhD student here at Johns Hopkins. So my question is mainly for John, and I want to ask for your opinion for this question. So in David's talk, there's a question that said that if people didn't pay attention to the task, there would be no 1 Hz oscillation. And in the end of the John's talk, he proposed that for implicit learning, there is a conversion between explicit that will convert it to an implicit, and there you will learn. So I want to ask John, do you have any opinion on the second level what or even third level how this conversion between explicit and implicit happening, and how can attention or this explicit understanding help the learning?
Yeah, I mean, I've worried about that a lot, and I think that maybe the word conversion is bad, because it suggests that maybe you are taking one thing and transmuting it into another. Whereas you could imagine some kind of, this is completely conjectural, it's sort of internal thing where you do have a model-based explicit representation, right? And then that turns into a kind of input to another area that does statistical learning, for example, on it, right? In other words, it's not so much that this turns into that, but it forms the basis of an input to another system that learns in a completely different way. So I'm beginning to suspect that it's not like you lose the, although, you know, it's interesting, I don't know my ATM number. Now that they've switched to 4 numbers, I'm better. But whenever I traveled and the ATM pad was different, I'd have to go online, look up an ATM pad in the US, remember and do my finger thing, and then get the number from that and then do it. So I say that just because at that point it looks like the explicit knowledge that I once had of my ATM number is now gone, or not gone, it's not retrievable. And now I've got this other thing that takes its place, but I can retrieve the explicit number with a clue. So my guess is one trains the other, but they're separate, and one doesn't actually convert into the other, is my suspicion now.
Thank the speakers again for
Okay. Thank you.
So we're going to take a break for lunch until 1 o'clock.
Wonderful. My fellows and
Yes. Let me just turn all this off.
I've made a lot of changes.
Not as resolute. I don't know what they want. Interesting. That might be there.